This is CS147 Computer Architecture Lecture 15. This is basically the second part of the pipeline architecture study that we started on lecture 14. This is a continuation from that. Uh, we have these three topics. Two are major, like data hazard, control hazard, and last is important but not touched in detail, pipeline implementation. Pipeline implementation is a complex subject itself, and possibly it's a candidate for a master level study. So we'll just look at the outline of the idea, how a pipeline can be implemented, then we'll just leave that topic from that. So we'll just review that at a very shallow level, how a pipeline can be implemented, and then we'll just rest for it, the pipeline architecture. If you guys are more interested, I hope our master's level study, which is 247, picks up this pipeline implementation area and discuss in more. Might want to pick up that. All right. So we talked about three type of hazard, right, in the last lecture. Structural hazard that we have already addressed and resolved the structural hazard. Then next category is data hazard, and another category is the control hazard. So data hazard is basically it is coming from the relation between the operands in different instructions. What I mean is that when we are processing or running a program, usually we compute some variables and compute value of some variables, and that updated value to be used in the next set of instructions, so on and so forth. So one instruction completion is really depending on another instruction's completion. For example, like if I had these two instruction, add R1, R2, R3, which means the first instruction is adding of values in register 2 and 3 and making the result at this register 1. Then instruction 2, which is sub R4, R1, R2, which is basically subtracting value of R2 from R1 and putting that result into R4. So really the underlying notion or intention of the programmer is that this the first signal that add instruction is completed first, so that R1 has the updated value of the addition, and then that updated value being used at the second instruction, right? That's the programmer's intention. Now you see that your R1, when it is fetched from the register file, okay, it is for the second instruction, it is at second one to third cycle, basically from the beginning. If you calculate, this is between 3 nanosecond and 4 nanosecond. This is the second cycle of the second instruction, which is aligned with the first third cycle of the first instruction, right? So at this point, your R1 register value is accessed, right? That is the instruction fetch stage. But your updated value of the R1 will be available only at the write back, after the write back is done, right, of the first instruction. So like in the write back stage, this is the only stage when we commit the result to the register file. So that means your updated result from the first instruction is available only after 6 nanosecond, right? Whereas you are trying to access the updated result at the beginning of the 3 nanosecond. So in this window, 3 nanosecond to 4 nanosecond window, you are trying to access the updated value of R1, which is not yet available, right? So what you are accessing at that point is the old value of the R1. So definitely, if we keep our execution like this second instruction is not going to produce the intended result, right? So we need to do something about this, and this is what the data hazard means the result of instruction 1 is used in the another instruction which is not yet committed into the register file. That's the problem. How do we solve it? Of course, our first intuition is to, well, I wait till my result is available in the register file, which is after 6 nanosecond, and then we start the second one. Well, that defies the whole purpose of the pipeline, right? You are just going as if it is kind of a sequential execution of these two instructions, right? And if you think your programs, like if you list your instruction in the program, actually your successive instructions are depending on data crunch from the previous instructions, right? So this case, this scenario is pretty common, and probably for most of the instruction you need to wait till write back stage is done. So you are just throwing out the advantage of pipelining. Okay. Oh, by the way, just to make a notation, this bubble means here this nothing is done in this during this time, right, for the next instruction, and next instruction being started from the after the first instruction is end. So bubble means we are stopping there basically. Now the solution of the data hazard is first technique is data forwarding, okay, and which means you see that we look at where in which phase this data or updated register value is accessed, which phase it needs. So we know that updated value at the earliest possible time, okay, is needed in the beginning of the third cycle of the second instruction sub. So updated value of the R1 is needed at the start of the third cycle of second instruction, which is at beginning at 4 nanosecond. Okay. Now we see when this value get updated. So this value of R1 or updated value is available, the updated value of R1 is available at the end of the third cycle of the first instruction, right? That's when we are adding up this value from R2 and R3, and that addition value is ready, even if it has not been committed into registered file, which will be eventually done at the write back stage between 5th and 6th nanosecond. But R1 value, the updated value of the R1 is available. The idea is that as soon as this value is available, we can forward it to the next instruction. So here in this problem, this specific problem, what we'll do, we through some mechanism, don't worry about the mechanism right now, right? How it is done, that's not important. The idea is important that as soon as my updated value is available at the end of the execution cycle of the instruction 1, we'll take that value and use it into at the beginning of the third cycle of the second instruction, exe cycle of the second instruction. That's where the value is being used. Updated value needed to be used in that subtraction instruction. So we are taking the value from the end of the third cycle of the first instruction and use that value into at the beginning of the third cycle of the second instruction. So this is what we call a data forwarding. Now let's look a little bit one more step. Let's say we involved another instruction, and which is sub R5, R1, R3, and this guy also has a data hazard, because you can see that when we are accessing the register file for the R1 doesn't have updated value because it will be updated during 5th and 6th nanosecond, and that updated value will be available after 6 nanosecond. So clearly the third instruction also has a data hazard. But what we can do, we can still forward this value, keep forwarding this value to the execution cycle of the third instruction as well. So we are producing the updated value for the R1 at the end of 4th nanosecond, and we are using it to the second instruction at the beginning of the exe cycle, which is at the 4th nanosecond. And also here we can use the same at the beginning of the third cycle of the third instruction, which is at about 5 nanosecond, because the data is available. Now take another case like this one. Okay, we have a load word R1, R2, and some offset, and then we are doing subtraction of R2 from R1 and putting that result into R4. Now here in this case, we are producing the value at the end of the memory stage. It is not producing the value of at the end of the exe stage, because it's a read memory operation. So we need to wait till memory operation is done, which means the updated value of the R1 will be available at the end of the memory cycle, which is at 5 nanosecond time, right? But you are trying to use the updated value at the 4th nanosecond, which is start of the third cycle of the second instruction. Clearly in the timeline, your data is not available, right? You cannot, this is not a time machine. You cannot just go and fetch something from the future, which has not happened yet. So in this case, data forwarding is not possible. It's absurd, right? So your data is updated data available only at 5th nanosecond, 5 nanosecond time, but you are trying to use that updated data at the 4 nanoseconds time. So that's not possible. Physically, that's not possible. So data forwarding is not possible here. There we go for the stalling the pipeline. So what we do here, instead of wait till the write back is done and then start instruction fetch, etc. for the next instruction, what we do, we halt the instruction for least amount of cycles, such that your temporal relation becomes in phase. Means that we can forward the data from the previous instruction to the next instruction. We just minimally we kind of push the instruction execution such that when you need the data, really updated data, which is at the beginning of the exe cycle of the second instruction, that time at least falls about the same when the data is produced, which is from the data production instruction, which is in this case instruction 1. Now you see, if I just stall for one cycle, somehow shift this instruction for one cycle, then what will happen is this: my data is produced at 5th nanosecond, 5 nanosecond, and data is, we are trying to consume that updated data at the beginning of the 5th nanosecond. So they are on the same time. So I can just produce and give it to the next instruction. So data forwarding is possible. So in this case, instead of stalling for 5 cycle complete to wait for write back to happen, we just stall for 1 clock cycle and shift the execution of the next instruction such a way your timeline of data production and data consumption becomes in phase with each other, so that we can forward that data.